Hey there. I am going to explain you today about the famous Bayesian theorem in the context of the Monty problem. Let's get started. Let me first tell you what is Bayesian theorem all about. Probability of A given B is equal to probability of B given A into probability of A divided by probability of B. Probability of B is also written as following using the law of total probability rule. Here, probability of A, that is P of A, is called as prior probability, the probability before having any evidence. And probability of A, given B, is called as posterior probability, the probability after we get evidence or new piece of information. Let me tell you the simple intuition of this theorem. Let us say it's been so long you and your friend not seen each other. One day you were in market and suddenly you are seeing someone who is at distant and looks like your friend but you are not sure. Here, since the vision is not clear due to the far distance, your mind thinks maybe he is your friend with some probability. Let us say probability of he is your friend is 0.5. Now he started to come towards you, and your mind update the probability as he is approaching and giving the piece of information or evidence. When he is coming near to you, the probability changes from 0.5 to 0.7 until 1.0 if he is your friend. The simple thing I want to tell you here is this: your hypothesis updates with the arrival of new piece of information or evidence. Now, let me explain you what is Monty problem. Suppose you are on a game show, and you are given the choice of 3 doors. Behind one door is a car, behind the others, goats. You pick a door, say door number 1, and the host, who knows what's behind the doors, opens another door, say door number 2, which has a goat. He then says to you, do you want to pick door number 3? Is it to your advantage to switch your choice? Remember, you don't know exactly what is behind each doors. Having this explained, let's jump into using Bayesian theorem to solve this problem. Initially, you don't know which door to pick. This problem can be considered as random process, because if you select any of the doors we may have goat or car behind it. Since we cannot certainly say what it's going to be, it is a random process, and here we can use probability, especially Bayesian framework, to understand the problem. We can define sample space as set of these 3 outcomes shown. Let us define 3 events as following. Event C1 is defined as event that the car is behind door number 1. Similarly, we can define events for other 2 doors as shown here. These events are mutually likely, meaning they have equal probability. That is, probability of C1 equal to probability of C2 equal to probability of C3 equal to 1/3. Before observing any evidence, prior probabilities are as shown in the picture. Probability of car behind door 1 equals probability of car behind door 2 equals probability of car behind door 3 equals to 1/3. Let us assume you pick the door number 1, and you don't know what is behind it. Now, game host opens one door from the other 2 doors. Say, door number 2, and shows the goat behind it. Once we select the door number 1, game host can select any one of the door from the other 2 doors to reveal the goat. We don't know which door he picks to reveal the goat. Again, we can think this is a random experiment of selecting one door between door number 2 and door number 3. We can define sample space for this random experiment as set of door number 2 and door number 3. Let us define events as follows. Let D2 be the event of selecting door number 2 to reveal the goat. Similarly, we can define other 2 events for door number 1 and door number 2 as shown here. Now, our task is to find probability of goat behind the door number 3 given that we have selected door number 1, and game host opened door number 2 to reveal the goat. It can be written as P of C3 given D2. Using Bayesian theorem, we can write equations as shown here. Let us compute the numerator part and denominator part separately. The calculation of the numerator part goes as follows. P of D2 given C3, that is probability of game host opening door number 2 to reveal the goat, given car behind the door number 3, is multiplied by probability of car behind the door number 3, written as P of C3. Given the car behind the door number 3, the probability that game host selects the door number 2 to reveal the goat is 1, because he is left with only door number 2 to pick up to reveal the goat. Probability of car behind the door is 1/3. Multiplying both the components, 1 multiplied by 1/3 gives us 1/3 as the numerator value. Let us now compute the denominator part. Using the law of total probability we can rewrite denominator as shown here. As we know P of C1 equals to P of C2 equals to P of C3 equals to 1/3. P of D2 given C1 is equal to half. Because given car is behind door number 1 and probability of game host opening the door number 2 to reveal the goat is half. P of D2 given C2 is equal to 0 because given car is behind door number 2 and probability of game host opening the door number 2 to reveal the goat is 0. P of D2 given C3 is equal to 1. Because given car is behind door number 3 and probability of game host opening the door number 2 to reveal the goat is 1. Finally, computation of denominator value becomes half. Putting numerator value and denominator value into the base formula we get 2/3. So, probability of car behind door number 3 given the game host opens door number 2 to reveal the goat is 2/3. Here, game host is giving the evidence in the form of opening the door number 2 and revealing the goat behind it. Before having any evidence, the probability of finding car behind the door number 3 is 1/3. But with the given new piece of information or evidence, that probability changes to 2/3. More concretely, it is better to switch the door to get the more chance of winning car. Probability of car behind the door number 3 given the game host opens the door number 2 to reveal the goat is 2/3. Similarly, probability of car behind the door number 2 given the game host opens the door number 2 to reveal the goat is 0. Using the probability rule we can compute the probability of car behind the door number 1 given the game host opens the door number 2 to reveal the goat as 1/3. Because individual probabilities sum to 1. We can conclude, no matter which door you pick up and no matter which door game host opens to reveal the goat, always switching gives us 66.66% chance of winning the car. Now, the posterior probabilities can be visualized as shown here. From the graph we can say giving the evidence, 1/3 probability adds up to the other unpicked door from the door game host opens to reveal the goat. We input the prior knowledge in the form of prior probability distribution and, with the evidence, our prior probability updates to posterior probability distribution as shown in this formula. This graph shown here is for continuous probability distribution. Red curve on the right shows prior probability density and, with the piece of evidence, this probability updated to posterior probability density as shown as shift the graph towards left. This is the only one instance of application of Bayesian theorem. There are many other important real-life applications of Bayesian theorem. Thanks Thomas Bayes.